Firstly, welcome everyone to tonight's webinar, where our speaker, Susan Krumdieck, will discuss carbon and energy transition in 10 years' time. So Susan is originally from Colorado, and she studied mechanical engineering and went on to do a master's in energy systems engineering. She took an academic position in New Zealand in 2000 and was the first woman promoted to full professor in engineering at the University of Canterbury. Susan's research experience has been wide-ranging, with more than 160 peer-reviewed papers in subjects like energy and transport adaptation, renewable energy, and energy for remote communities. So I'll hand over to you, Susan. I'm sure it'll be a very interesting talk. Thank you.
All right, well, thanks for having me, everyone, and glad you could sacrifice your evening out at the pub. Oh, bad joke, sorry. All right, I am going to share my screen, hopefully. There we go, I want to share it that one. Thank you.
You're sharing.
And we've got it?
Yeah, it's good.
Sweet. Yeah, you'd think we'd have these things all figured out by now, wouldn't you? All right, you're seeing the right view, yes?
Yep.
All right, cool. All right, I'm going to talk about transition engineering today. This is an emerging field, I would say, even though it has been a lot of years in the research mill and the trying things out and seeing how we go, learning, improving. But now we're ready for launch, which is good because we are at that last moment of opportunity to do such things. And I have done this work at Canterbury University, and I will be transferring this work to Herriot-Watt University when the COVID allows. So this evening, we are going to undergo a revolution. So it's a revolution in 4 parts. Why a revolution? Because, as you can see from the spaghetti on the right-hand side there, these are the RCP scenarios from the IPCC modeling of trajectories of emissions and what that does to the planet. And you'll be familiar with it. The one we're all meant to follow is the one on the bottom, the purple trajectory, to just overheating the planet, not cooking the planet. And so this revolution is really, that's the point we're at, turning a corner, doing something different, because business as usual is not working. So the way we're going to do that is we're going to change the ending first. If you're watching a Hollywood movie, you would know how it's going to end, usually, right? They save the world. So we're going to have to do that. Then defining the problem is important in engineering. If you don't have the problem definition right, you are not going to solve it. Then how are we going to get it done? And how are we going to create real value? Because if we don't do that, we won't get paid, and therefore we'll continue on with business as usual. So here's our first part. How do you change the ending? You might recognize this ship. You know what's going to happen, right? You know what's happening with the Titanic. And so we're going to do a mental experiment to see if you could change the ending. I have a time machine. It's the 12th of April, 1912. It's 5 a.m. and I have transported you with my time machine here. I put you on the first class deck of the Titanic because I thought maybe you'd enjoy that. But you've got a few hours before you know what's going to happen. So what do? What's your first impulse? What do you want to do? Get off that ship. Not a bad idea. But you're in the middle of the Atlantic at this point, and nobody knows where you are, and you're in a little ship. I don't actually like your chances going it alone, lifeboating. Sailing off to New Zealand and getting your own piece of paradise to wait out this conflagration. So don't do that. We got to change the future. All right, changing the future. What does that look like? Yes, I'm talking metaphorically about our economy hitting the iceberg of 2 degrees C, etc. Yes, that's what I'm talking about. So, question, are we doomed, right? So was the Titanic doomed? Well, not if they didn't hit the iceberg. Am I right? Don't hit the iceberg and you're okay. Is that possible? Could they have not hit the iceberg? You're on that ship. What would you do to slow down the economy, or the economy? Slow down and change course. What would you do? Is it that they don't know? Is it that the scientists haven't done a good enough job of explaining to us what happens if one hits an iceberg? Is it that the information isn't known? And the truth is, no, the information actually is known. The telegraph operators got 14 messages from other ships explaining what was going on in front of them and pinpointing the iceberg that they slammed into at full speed. They knew. Somebody knew. The telegraph operators knew. It appears that maybe they didn't relay the very last message they got, which pinpointed that iceberg, because they were so busy sending telegraphs of the first class passengers to their friends in New York and London, telling them about how great their journey was. But yeah, okay, little social media noise there happening. How about the navigators? Well, the navigators of all the ships in that corridor that day knew where those ice flows were. So the navigators stayed the course. Was it their job to change course? Well, not really. It would be the captain's job. So did the captain know what was going to happen? Did he know the risks? And the answer is obviously kind of yes. He did actually make a course correction, just a tiny one, went a little bit south, ordered a southerly direction. The sea was perfectly calm. It was a beautiful, clear night, and he went to dinner. So could we get to the captain and like explain to him, you know what, you really have to slow down this ship. Okay, I don't know about you, but if we're on this Titanic, what are the odds that we could actually get a discussion with the captain? It's kind of like with our political leaders. We think they kind of know what's going on and what they should do. And yet, you know, you want to talk to them, you want to say, yeah, but you can't. You can write a letter. Who knows where that goes? All right, let's try something else. The owners of this ship are going to lose their investment, right? And this guy, Bruce Ismay, he was on the ship. He did survive. But, you know, maybe if we talk to the financiers, if we talk to Wall Street and said, look, it's actually going to be better if we slow down the ship. But wait a minute, haven't people already done that? Haven't they explained that actually the cost of climate change is going to be way higher than the cost of slowing down the ship? Okay, how about the first class passengers? You know, they have all this money. We could go talk to Jeff Bezos and Elon Musk, somebody, and say, it's not that we don't have enough electric cars that is putting us at risk here. We have so many fancy things on this ship. It's that we have to slow this ship down. Otherwise, you're going to be cold. And actually, Mr. Strauss, you're going to be dead. So yeah, even the 1%, you couldn't save all of them. Again, sorry, we can't actually get any contact with those people. So how about the third class passengers, the people down in the bowels of the ship? We can definitely go have conversations with them, but it's getting late. The kids are cranky. They're cramped. And they're like, look, just we're going to bed. We're tired. You know, it's a long voyage. It's 4 days. Yeah, but we got to go up on the deck and occupy. We got to protest. We got to get them to slow it down. They're not hearing us. Like, yeah, okay. So the masses don't seem to be able to be moved. They do care. They don't want to die, you know, but doesn't seem like today is a problem. How about the architect? How about the guy who actually designed this thing and designed it to be unsinkable? It's a really good ship. I mean, nobody says it isn't. But what if because he probably does have access to the captain and the first class passengers. What if he actually came out and said, you know, while the ship is unsinkable, it's really good, works great. There actually is a risk if we went full speed into an obstruction. You can't actually just sail this thing full speed into. Would that help? If the people who actually designed the thing explained that we actually have to slow down, would that help? Well, again, we can't find this guy, and he does not want to say that. Think about how much courage it would take for you and your great thing, your great thing to actually say, I think there's a risk here. That we got to be careful. Are we out of options now? Luckily, you engineers know thermodynamics and you understand steam engines. And so actually what is making this ship go so fast. So we're going to go all the way to the bottom of the ship where there's 52 guys shoveling coal as fast as they possibly can. You're going to go to the engine room, go to the foreman and say, look, we got to slow down the ship. Not reckless, right? We're not going to throw the doors shut. We're not going to do anything that's going to put the ship at risk, but we are going to slow down, pull the handbrake, back it down, and the ship will slow because we're not burning as much coal. And probably nobody will even notice because they're all asleep anyway. And then, they only had about a minute and a half after the iceberg was spotted to try and slow down the ship, and it was way too late then. And so the engineers are a little bit worried because, look, we get paid to shovel. We do whatever the captain says, right? So if we don't do that, we could get in trouble. And that's a good question. This actually is a revolutionary, game-changing moment where the people in the bowels of the economy decide to not do something. All right, so the engineers could save the ship. They could do it by deciding to do it. They could do it by taking courage, maybe joining together, and they could do it by following professional practice. Don't sabotage the ship. Don't blow up the engines. Back it down. So that's our problem, preventing what's preventable by changing the systems we know in the way that's required. What is defining the problem? Well, prevent what's preventable, don't fail. And when we look forward and we look at the data and we look at all the stuff the scientists are telling us, it is absolutely clear that there is a turning point, a transition period, turning a corner, however you want to phrase it, something really big happens in order to avoid the failure limit of the climate. Now, this target of 2 degrees C, please do not use the word target for something that will crash the ship. That iceberg is not a target. It's a failure point, all right? So we're not going to crash into the 2 degrees or even the 1.5 degrees. And that means we actually have to stop putting fossil carbon into the atmosphere, which means we actually have to stop producing oil and slow down the ship. And that is a really big job. The rate at which we have to do it is a 10% retreat per year. So think about the oil industry. If any of you know the oil industry, the work of figuring out how to produce 10% oil next year compared to this year, that didn't go that well this year, did it? It's going to require engineering from people who know how that system works in order to get it done. Because here is the requirement, the engineering requirement, the definition of the problem for all engineering work. Wherever you are, whoever you are, 80% downshift in fossil fuel by 2030, that's your job. And it goes lower than that as we go on. But good news, the good news here is that then there will be oil later to use because the bit that we are using is important. And it's going to look important when we use it, not sort of what we do now. But so those downshifts, there's room for this downshift. Believe me, we can do it. Now, okay, if your brain is hurting, that's because oil is a wicked problem. Wherever it is in the economy, we use oil, it will be a wicked problem. A wicked problem means there's no solution. There's only changes. And the way that we attack wicked problems is that we have to get right to the heart, not of what we are doing now, because that's why it's wicked. We have to get to the heart of what's important. What is the essential need that we're actually fulfilling? So like with oil, driving in cars isn't an essential need. Accessing activities is an essential need. Going to work, getting to school. Well, now start over, start thinking. You have to get out of these wicked problems in order to make any head way. Why are they wicked? Because we can't approach them correctly, right? We know we're using 100 million barrels of oil per day. If that oil supply stops flowing, even a 10% reduction. In the UK, there've been a few episodes, the lorry drivers strike, that actually was about a 10% reduction in fuel supply. More than $1 billion worth of economic damage, panic, mayhem, soccer games weren't played. It was crazy. So we know our systems fail. We know they're not robust. We know we haven't designed them to manage reductions in oil supply. Guess what the job is now? But because if the oil supply does keep going, if we keep doing what we're doing, then we're done. We failed. So the process of working through a wicked problem is a parking and unpacking. It's more of a psychological process, but this can be done with stakeholders, with businesses, with anybody. And it's basically, you just put this diagram on the table and work through, why does it work great? Why are we doing it that way? Why is it not sustainable? What needs does it actually satisfy? What harms does it cause? And that's not climate change. Unsustainability is climate change. Causing harm is crashes, pollution, ground level air pollution, NOx, this sort of thing. Understanding that this system must change in the future. It has changed, therefore it must change, but right now it can't change for a lot of reasons. So this parking and unpacking is a methodology explained in my book that just came out at the end of last year, and it works great. We have done this with business people, with communities, with engineers. This is a great little exercise. What it does is it takes the wicked problem from where it's blocking your brain and puts it on the table where you can now work on it. And that's the next part of the job, is to just get this thing done. What will all these transition engineers, and who are the transition do, and who are the transition engineers? Now this one's interesting. You may have been, or you may be a sustainability engineer. You may be somebody who cares about sustainability, which is why you're one of the people who signed up to this this webinar. Well, transition engineering is actually the job of all engineers, not just the sustainability ones. And this is a revolution here in itself. That's going to require carbon and unsustainability literacy, not sustainability. We've already got those people. And it is going to require transition due diligence or duty of care, however you think about that, that thing that professional engineers do. They're now doing it around this transition, this big change. And that's going to require a flipped perspective, thinking about things totally the other way around. So in transition engineering, we get quite good at that. Take your hands, go, okay, I see it this way. Let's flip it around the other way. And innovators, product designers do that a lot. All engineers can learn it, and that's our next thing. So what do I mean by flip it around the other way? Well, top down is the stuff we're used to hearing all the time on the radio, on the news, the COP21 Paris Agreement, the COP26 coming up meeting, and people will talk, and there's the climate change commissions, there's net zero acts, there's policy level stuff, and CEO declarations. We're going to go carbon neutral, yeah? And so you've got all that, and that's fine. Where we're talking about transition engineering is from the ground up. The systems that are producing and burning fossil fuel are on the ground, and that's where we work. So that's within our local councils, our communities, companies, organizations, farmers, fishermen, whatever, from the ground up. And that means we have to do projects. We have to be able to measure performance. We have to understand returns, benefit cost ratio. And somewhere in the middle is where the two meet. And that is in the space where we live. So also quite close to the ground, but now connected to other things with other systems. So I hope you can understand that perspective. You understand we're talking about wicked problems, which means I don't even know what to do next, right? Well, that's where, as engineers, we are used to being in this space where I don't know what to do next is. That is what we spend 4 to 5 years at university learning how to deal with. If I give you a thermodynamics problem right now, figure out the work produced by a steam engine, blah, 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 blah. You're like, I got a book here where I know how to, I set it up. Yeah. find the amount of heat that's transferred through a wall of a boiler. If it has it, okay, we can't do it off the top of our head. We have methodologies that we follow. That's what we're taught in engineering school. What those methodologies do is that they do work. They apply the science, you know, free body diagrams, circuit diagrams, all these things, state space analysis. But mostly what they do is they let us chill. I know I can do this. I know I can't do it, but I know I can do it. So guess what? We got a methodology for transition engineering. It's called the interdisciplinary, because it doesn't matter what flavor of engineer you are, this is your method for transition. Interdisciplinary transition innovation, yeah, not like new gizmo type innovation, but innovation because there are no solutions, therefore something new has to happen. Management, because it has to be in a business context and a policy context. And engineering, because we're talking about the bowels of the ship. It's actually project work. So where we start, you can see that there's a number 1 there. That's the first project. And the first project is to get in your time machine and go back 100 years. Don't go to the deck of the Titanic. That's a bit, that one's harder. Go to wherever the essential need is in the place you're at. Remember we said from the ground up. So the wicked problem of the day in your place that you're working on, you go there 100 years ago and see how people were meeting that essential need, right? Why? Because we learn from examples. Human beings, and especially our type of people, the people who like to solve problems and think of ways to get things done, make things work, have always been doing that. And we can do it in any context, in any continent, with any set of resources. That is actually our survival strategy, is to be able to adapt to whatever we've got, fit within our limits, and make things work. All right. We're not oil man. This is a blip through all of human time, and we're going to get ourselves out of this. All right. So you can study history. Anybody can study history, and it's quite interdisciplinary to study history. So that's why we start there, because we can. We just said we can't solve wicked problems. So let's go back and look at history, and we learn so many things, and it's fun. History is always fun. Then you have to look at the system dynamics of how things have changed with time, because there's always a reason that things happened, and we have to nut those out. And then we get to where we are today. So that's project number 2. All of this is data driven. If you go back in time, you have to get the data or generate data or create data or understand data for that. And then of course, now we have lots of data. And we have the economic view is really only in the now part, because economics doesn't make sense outside of the current situation. So that's where the economics sits. And then the next step forward, going forward into the future, you're going to take a step, which means you might not do something, you might design a new thing, you might invest in something. And so you want to know, how are those going to play out? And that's where we take scenarios, things that policies might think we're going to do, things that anybody thinks you might be going to do, new technologies, and we road test them and crash test them. Because if those things aren't really what we're going to do, then we have to stop thinking about them, or we will be stuck again. This is why wicked problems are so sticky, because we keep getting stuck in places. All right, so there's a whole thing around how you do those. I'll show you a little example of one in a second. And then you've got to move forward in time 100 years and go explore your place and how people are meeting the essential need, essentially without oil, except for some very essential activities. And they're also regenerating carbon within soils and environments. And so go to that 100 years from now. And there's a whole process of doing that. And again, it's numerical. It's engineering view of 100 years from now. The most fun you'll ever have. And then you come back, of course, to where we are today, understanding that what we really went to the future for was to find out what they are doing, what they have that we don't have, because that's where we look for innovation, is what happens now that actually leads to that future. And I must qualify, the 100 years in the future is not, Not the one we're actually going to right now, but the one we choose to go to. Okay. Lots of Armageddons that are possible. Don't go there. That's not fun. And then all of this has to come out to be an actual project that you could do, a thing, an actual build this, change that, right? So projects, and those projects have to have learning curves. And we, from now on, transition engineering due diligence will include that we will look forward from what we do. We will look forward beyond the end of life of whatever it is we're doing. And we will look at the unintended consequences. We will understand what policy implications are, social infrastructure, you know. Okay, we always say, well, we look to end of life, you know, do life cycle analysis. Yeah, sure. But no, we're actually going to look. We're going to go there. And that's the new kind of economics that we have in transition engineering as well. Okay, is this a proposition? Is it an idea? Well, it's here, okay? For the last 10 years, I have been working with people from around the world, taking the stuff that we had developed through research, doing projects. We now are teaching transition engineering as a level 8 professional development course online. We have the textbook. It is being adopted around the world. It can be added into curriculum. It's not like it's a whole new department. It's not at all. It doesn't work like that. It's all engineers learning a new trick, right? And those courses have been going very well, and it's happening. All right, so that's great if engineers can do a new thing, learn a new trick, but who's going to buy it, right? We're talking about wicked problems. We're talking about, okay, we might come up with something, but then we have the inventor's dilemma. Who is going to understand what we're even talking about? How are we going to do stakeholder communication about this, right? Those engineers in the bowels of the ship, how are they going to explain to the captain that they just slowed down shoveling and, you know? All right, because this 7-step process is the same problem that you see here. It's the, we have this elephant in the room, and the scientists are measuring how much damage is being done to our furniture and our china and our goods. And they're like, you know what? The damage is really, you got to do something. The damage is accumulating and it's going to get really bad. And the people who then get that message are in this situation where they're all correct about the bit of the problem they're seeing, but together they're really not making much progress on an efficient way to get the elephant out of the room and back down to the river and into the jungle where he belongs. And I have mapped out over the years, this has been a engineering psychology project of when you're in a room with, I don't know, 20, 50 people, and you're supposed to be working on, okay, how do we have sustainable city? How do we build resilience? Anytime that you're working on something that you don't already know the answer, then this is what happens. You have some people who talk about well, you know, before we had this problem, or 100 years ago, or, you know, they always talk about how we did things in the past, and it's really hard for them to move out of that spot. Then you have people who, you know, well, we've already got a policy. So like our politicians looking at what we're doing, our economists, and then people saying, okay, what can we do next? And then some sort of dreamers, well, what do we want to become, right? What's our ideals? And then probably the engineers, very practical people, business people. Okay, but what do I do next? And what's the risks of that? How do I de-risk it? Can I get a subsidy? You know, real practical. And then we definitely will always have people telling us why we can't do any of that, right? What we can't do. And maybe they're right, because you can't just let this elephant move around the room anymore. We actually have to have a plan. Now, it might occur to you that all these folks here could take their blindfolds off and look at the whole thing and figure out, okay, let's get some peanuts and lure the thing out. And so that's what the 7-step method does, that you numerize that journey through to what we are actually going to do. And now you can take all these people with you on that journey. All right. So sort of sense making, communication, ideation, telling our own story. Okay, sound like engineering? It's okay, you'll survive it. Now we've got to figure out how to monetize this piece of work, because it is a lot of work to go through this 7-step method, do all the modeling you need to do the numerization, get the data, have the workshops, have brainstorming, test the concepts, and then of course to prepare this communication with people. And so we've got to add real value, or nobody's going to actually put this into the budget, the transition due diligence work. So adding real value is our last question here. And that I'm going to say that changing the future is worth doing. Yeah. And I'm going to prove that point by evidence. Here's the evidence. That ground up engineering change, from the ground up, not ground up into pieces, ground up engineering change has always worked in the past, and it has always returned value in the past. So like safety engineering did 100 years ago, we are starting from a point of abject failure. And we are deciding to prevent what's preventable. And when we do that, it's the decision that makes all the difference. I'm giving you an example here of 100 years ago, people who worked on electricity lines. Providing electricity was making people filthy rich, and it was providing really cool services that people hadn't had before in ways that were way less dangerous than lamps and lanterns and candles. And so it worked great. You had to do it. And yet somebody had to get up on those poles and do this work, and they were dying so fast that they couldn't keep training people fast enough. That's awful. And so when somebody finally took on the idea that this could be prevented, it wasn't magic. It was the idea that was magic. So look at the guy now, the lineman now, look at all the PPE he's got. That all had to be engineered. Not by safety engineers per se, but by regular old mechanical engineers, material engineers, engineers working on the physiology of if the person falls, how does the harness that they're in not actually kill them in the fall? How does it save them in the fall? How does their equipment interact with this high voltage situation and not fry them? That's all just regular engineering now put in place by the directive of preventing what's preventable. So we'll do our normal work, but with due diligence, with duty of care, to changing our successful systems if they must be changed. And therefore, our work will change the future and the value will be realized. All right. So if you buy this premise, always go back to safety engineering. Definitely go to the history of safety engineering, study it. That's what we're going to emulate. Because it wasn't just safety. We've done this so many times since then. Huge failure, corrective action, prevent what's preventable. Natural hazards, fire safety, waste management, air pollution, refrigerants. This is what we're good at. So now if we take on this job, which we will, because now we have a way to take on this job, the future will be all right. That's why I can smile. That's why I can get on with my day, because I know there's a way, and it's not hard, and I can teach it to you in a short order. Now, I told you I would give you an example of why this, why transition engineering will pay for itself. And one of the best ways to pay for yourself is that you help with the risk management, and you help with the investment planning, and you help with understanding where good value is for investing. And so that's in this step 3, looking at things that we might do right now and how they play out and crash testing those. So that means using accurate engineering information. And in a lot of policy development right now and investment decisions around that, we're not really seeing a lot of accurate information being used. So one of the tools that we use is energy return on energy invested, or just energy analysis, net energy analysis. Just do the analysis. So this is a little exercise in that we set up We can imagine a 100 megawatt wind farm. That's not hard to imagine. We have wind farms even bigger than that in New Zealand. And in New Zealand right now, if we added 100 megawatts, it would be surplus energy because we don't really need it right now. And so we could use that surplus energy interacting with 730 megawatts of primary resource, the wind. That's the wind power you have to go out and get. You have to build a capacity of actually 343 megawatts in order to get your 100 megawatts of production because of the variability. So I got my 100 megawatts of production, and my society, my economy, had to invest 5.5 megawatts worth of embedded and operational energy in order to get the 100 megawatts of production. We lost 15 megawatts in our transmission. We've got a long stringy grid. And we got, for our economy, net 68 megawatts to play with, right? And so our economy is working pretty good. We've got lots of energy we can use there. And it only costs about $1,600 a kilowatt to do that, to make that decision to invest in that. So that's working pretty good. Now, EROI on this, energy return on energy invested, the 68 that we got to the economy to do our thing, that's the good stuff, compared to the 5.5 that the economy had to invest to get it. And that's an energy return on investment of 12, and that's not bad. That's about the same as other electricity sources. Okay. Now let's look at other things. So I've still got my 100 megawatt wind turbines. I know that was a profitable thing to do, but I'm worried about that it's variable. So I'm going to check out using hydrogen as a storage. So I'm going to use electrolyzer, I'm going to compress it, I'm going to put it in storage vessels, I'm going to put it back through a fuel cell. So now I have to invest in electrolyzer, compressors, storage, fuel cell, and I just use the actual numbers that are published and are known for what that means my economy has to invest in order to use the wind in this way. And I've still got my transmission losses. And so what I see is that my wind power with hydrogen storage and fuel cell re-electrification gives me a net to my economy of 26 megawatts to play with. I don't think I'm going to see growth with this net energy. I'm going to have to reduce demand in order to use this. I don't get 68 to use anymore. And interesting enough, my economy is now doing more. The purpose of that economy is actually to run the energy system itself instead of to do whatever it was you were going to do with the economy. And so our energy return on investment is we get 26.5 megawatts to our economy. That was the good returned. And we had to spend 133 megawatts to get that. So we had to take energy from somewhere else as well. And why? Because that 100, we had to give away 40 some megawatts of energy that we had to use before, and now we had to invest those. So the energy return is not good. It's people say negative because they mean you aren't actually getting a return, and that's true, but it's not strictly a negative number. So this is just accurate information calculated for New Zealand. If we put in 100 megawatt wind turbines. Okay, when engineers say, oh, and here we calculated the cost. 10 times more cost for a fourth of the benefit. This is, okay. When engineers say, there are challenges to that policy, what they probably mean is probably not gonna do that. So we went ahead with this 100 megawatt wind turbine. We used our local generation utility factors, and we figured out that that could produce 126 kilograms of hydrogen a year. What size electrolyzer would you actually choose to do that? Because the idea is that you would use the excess wind, and probably the biggest electrolyzer that's been built is in the 10 megawatt range, and we've got 100 megawatt capacity here. So the other thing is that electrolyzers really degrade quickly if you ramp them. So this is, it's going to be a little challenging, but let's imagine that we could produce 126 kilograms per year of hydrogen with our wind farm. We know that there are cars that can use hydrogen. Current price-ish that you might be able to get it for $83,000, which would mean that could power 34,000 cars in New Zealand. Cool. Which is 1% of our current fleet. And it would cost $2.8 billion. So the people of New Zealand, probably with subsidies, want to spend $2.8 billion to do the same thing they're doing now. We have built wind farms that big. The wind farm cost about $440 million. There have been, since 2014, a little over 5,000 of these hydrogen cars built. The platinum that it would take to build hydrogen cars, if we used half of the total platinum production in the world, we could build, somebody could build, I don't know who, could build 4 million cars. New Zealand has 4 million cars, so we could replace all of our cars with hydrogen cars, and nobody else could use platinum. Well, okay, we could, I didn't take out the platinum from that's being used in catalytic converters for the rest of the world because, you know, but 4 million cars worldwide if you took all the other uses of platinum and put it into fuel cell cars. And there are no hydrogen trucks. Look hard. All hydrogen truck talk is computer generated images. It's just not a thing you could even choose. So when we say there are challenges, what we mean is, could we go on to something else? All right, transition works from the ground up. Transition engineering is wherever you are, just like all other engineering. Your streets, your HVAC, your vehicles, your electric power system. It's, you know, it's specific projects in specific places, given specific parameters of the same thing. So that's what transition engineering is as well. And you see here Male in the Maldives, the capital city of the Maldives. I've done transition engineering there. In Asia, done transition engineering there. And now I'm going to tell you about a simpler project, which is Christchurch, New Zealand. Is it simpler? Still wicked. So we went through the whole process, came up with shift projects. That's that actual project you would do. And the calculations of what is the investment, what's the return, how do you roll it out, how do you communicate with people, how do we get unstuck from that wicked problem of that 95% of the trips in Christchurch, New Zealand, 330,000 people, about 20 kilometers across, are by car. How do we get past that? And so our first project that we would put in is a tram network. Well, not a network, one piece of the tram network that we will eventually have. It runs down a corridor that goes from the University of Canterbury, which is kind of right at the where the two tram lines meet. University of Canterbury, 30,000 people a day coming and going from that spot. To the south, below that is a big industrial area, and to the right is a really big retail area down that corridor. Then we have our big park, and then we have our CBD. So this tram line runs down through the CBD into all of these. There's a really heavy activity system loading in here, which is why the traffic is diabolical. Right. And it's all, these are, each of those legs is about 6 kilometers long. So it's all bikeable, by the way, especially with an e-bike. But a tram plus cycling plus the little red dots are Go-Get share cars. If you don't know what Go-Get is, Google it. They've been running for 12 years in Melbourne. And so we have data we can use of how it works when you have an effective public transport system, you have access to share cars, and you have bikeability. And we can see the future in numbers. So this little example of this area, 33,000 people just in this area join Go-Get. That would remove 31,000 cars from this little area. That's not everyone giving up their cars. It's mostly people giving up their second car and people who really can't afford to carry a car giving up their, or not giving up, but just going to a different lifestyle. As a disclaimer, my daughter has lived in Melbourne for 4 years and has never had a car. This works, I'm telling you. those cars, the share cars that you need, would save the people of this area $800,000. Okay. The 20 kilometers of tram, and we call it re-tram because there actually used to be a tram 100 years ago there. It costs about $300,000 a year in servicing the bonds and running it. So the deal's looking pretty good so far. And that tram line and the reduction in traffic actually provides access to activities for all 68,000 residents in this area. So this is a no-brainer, putting that tram line in. We know that where we're going into the future is that tram line, which is this one here from the airport down to the CBD and out to the industrial area, that tram line is one piece of the network that once we do the first one, then we're going to be able to do the rest. We know that tram network intersects with freight movement networks, and that what you can't do on the freight networks, you can pick up with small trucks. So essentially, we are net zero by 2030 by starting off with this first shift project and carrying on with the rest. We happen to run on hydro power here in the South Island of New Zealand, so we actually get to net zero. And we now have a bikeable city because the cars aren't there, which means we don't actually need the cars anyway. We're getting those share cars just for trips to the mountains or trips to carry something. This tram line, so the tram line is running right down this street here, starts to generate new kinds of transit-oriented development. People are concentrating around these areas, and this is University of Canterbury here, where actually it's this low-density single-family houses on quarter-acre lots, which are now student slums. And so we see a development, redevelopment of different form of the city once you have those trams in, and once it becomes apparent that that you don't actually need a car. The developers now coordinate with that, and the city council can support it through zoning. So this is actually a urban form redevelopment that we have crunched all the numbers on. We formed a social enterprise called From the Ground Up to be a development cooperative with people who want to invest in this mixed high street model. There's a lot of businesses that need to be right near the university as well. And so we know it's all doable. We know what the rate of return is. And so now we're ready to go on that. And so in conclusion, what do you got to lose? Why wouldn't we have this convergence of what we can do, unlock what's possible to do and get onto it, define the work that we want to do, put on the table the cost of doing the transition engineering, the same way that we would have on the table doing the other due diligence and duty of care work that we need to do. Train up. In order to do that, we've got to train up all of our professional engineers with essentially a safety training on transition due diligence. They've got to be literate in this. And then, of course, we'll have specialists who are really good at this inventive process and communication and that. That rapid training now with these online courses, it is possible to get all of our engineers trained up within 2 years, and the future changes. That is actually possible. Using this flip perspective, providing that rationale for how we work, we can all learn that. And this methodology itself is a transformational process that lets you work with the stakeholders, bring them along on what you've learned, and sort of get past the sort of swirl of stuff that we're really not going to do because it doesn't actually make sense. There's lots of other stuff that we can do, but we can't even talk about that because we're stuck in the swirl. So that's my conclusion, and I hope that has generated some questions.